10 years ago where I was in a similar position of starting a conference, setting up an institute, and there's always pieces which are a challenge, but there are other pieces which are incredibly rewarding and fun to make people work together from many different areas. And I very appreciate that the institute here brings people from many different areas working together. As the introduction from the Dean of the Faculty of Mathematics and Exact Science worried me a little bit, because the idea of error correction is that things are not exact, that there are imperfections, there are errors, and sometimes they let us astray if we don't take care of them and we don't correct them. So my talk will be to deal with errors, in fact to learn about them and to try to correct them. I was putting my talk together, and then I was putting pictures together, and then I got the picture of this set of stairs here, which are the stairs in a new building at the Institute for Quantum Computing. And when I saw this, I said, oh, this is very much kind of an analog of my talk on experimental error correction, in the sense that we aim to go very high, but we're really at the bottom of the stairs and we're starting to go up and to climb the place, which is the message of my talk. We can start to deal with errors, but we are not there in doing a full treatment of quantum error correction on the experimental world. So my talk will be divided in a bunch of different parts. First one is, if we want to deal with error correction, we have to understand what are the errors, what is the error model, and I'll mention some of the work that we've done in trying to assess this. In principle, it's easy. We can go and look at what goes wrong, we know the error, and go on. But it turns out that in practice, this is very hard, and I'll explain why. Then I'll give example of implementation of quantum error correction codes that we've been able to do. And then I will mention about algorithmic cooling, and this will be focused mostly in mind frame of NMR or maybe ESR also, where we have to extract entropy. If we are able to do projective measurements, then we are in some kind of magic way extracting entropy of our system by projecting in a given state. In NMR, we're not able to do this. We'll have to find a way to extract entropy. I'll mention how does that work. And finally, I'll talk about magic state distillation, a way of purifying certain states, and you'll understand how this come about, and then I will conclude. About 15, nearly 20 years ago, in fact, maybe later than this, 30 years ago, people started to suggest that using the laws of quantum mechanics to manipulate information might allow us to solve certain problems that are intractable with using the laws of classical physics. Then we found some interesting problems that can be solved with these quantum computers. And one of the challenges of these ideas that were very interesting was, what would happen if we tried to turn these ideas into experiments and try to build these quantum devices? And what we've learned is that we would have to deal with errors. Naively, if we have errors, if we make a gate in a quantum computation, which is imperfect, with a probability of failure epsilon, then the probability of getting the right result is 1 minus epsilon. And if we have n gates, the probability of success will be 1 minus epsilon to the power n, and it will decrease exponentially if the errors are independent from gate to gate. And thus, the exponential gain that we thought we would have with quantum computers will be decimated by these errors. Fortunately, people thought about a way of doing this, which turns out to be very similar to the way we're thinking about it in classical error correction, or the classical world using classical error correction. The idea is to encode our information in some part of the Hilbert space in such a way that the noise that affects these particular states can be reversed using a recovery operators. We can do this in a way which is resilient to noise. That is, all this operation can be done in a fault-tolerant way. So even if there are errors that occurs while we try to correct errors, then we can take care of them as long as the error rate is not too large. Then we can use these codes, this encoding, concatenate them, and we are led to a theorem which is called the accuracy threshold theorem, which says that a quantum computation can be as long as required with any desired accuracy, the one that you want, using a reasonable amount of resources as long as the noise level is below a threshold value. And so the first question that you might have is, what is the value of this threshold. And on purpose here, I've made it very pale because we don't know exactly what this value of this threshold is. It depends on what the assumption that you have, which device that you have. And so if you are have very good glasses, then you can see here I had 10 to the minus 6, 10 minus 5, minus 3, minus 2, and sometimes people have suggested it might be as high as minus 1 if the error are very tame.
I agree that it's less than 10.
It's because you need a better pair of glasses to see it's 10 minus 6. So
it's also less than 0.
It is less than 0. So there's a threshold value, and it depends really on kind of what kind of code, what kind of device that we have. But roughly the number that people mention is 10 to the minus 4, 10 to the minus 3. Although I think the first number, one of the first number that was mentioned, I think was from the work of Dorit, which was 10 to the minus 12. If the errors are totally coherent, then it could be as much as 10 to the minus 12, which made all the experimentalists at the time kind of getting a gasp and saying, we will never arrive there. Fortunately, if the errors are not coherent, incoherent from one gate to the other, we get kind of the square root of this, which gives you values about 10 minus 6. People have improved the value of this threshold and give ideas of might be better. But again, it depends on what they are assumptions, which I'll come back in a few minutes. The significance of this is that, at least in principle, some imperfection and some imprecisions are not fundamental objection to quantum computation. So there might be a way, or there is a way, that might be implementable in experiments where we can correct for errors. It gives a criteria for scalability. In the world of physicists, they often think about scalability with the following ideas. If we have 1 qubit, we can produce 2, we can produce 3, and then we have an architecture with the number of qubits increasing. This is scalable. But there's more to scalability than just having qubits. There's many qubits. If you're interested in nuclear spins, there's many qubits in a glass of water. The question is not having a lot of qubits, but to be able to control them. And so this threshold gives us a set of rules and kind of criteria of when it is scalable. It also gives a guide to experimentalists, so that if you want to have devices which grows up and scales, again, error correction is a guide to make this happen. And finally, it's a benchmark to compare different technology, because it's something that will be used in all technology, and therefore compare one implementation to the other. But what I've been interested very much is what are these ingredients for the accuracy threshold theorem. And the first one which cannot be negotiated, is parallel operation. So if you cannot do parallel operation on a set of qubits, we do not know how to make it resilient to noise. So if you have a device, and for example, the original idea of the ion trap, where there's a single bus mode which connects all the ions, we know that this would not be scalable. It doesn't mean that you cannot learn interesting things by doing ion trap, but what it means is that we do not know how to scale up, and there's different ideas about how to scale this. We need to have good quantum control, and how good this control is the value of this threshold that I mentioned in the page before. We need the ability to extract entropy, as I mentioned before. The noise will increase the entropy in your quantum system. You'll need to be able to take this off. And finally, we need to know what is the noise. If you want to protect yourself against the noise, you need to know what the noise is. And I'll come back to how do we learn this in a few minutes. For example, in the threshold theorem, quite often we assume that there's no loss of qubits. Now, if you do lose qubits, it doesn't mean that you cannot do quantum error correction. It just means that these values of the threshold will change. We assume that there are independent or quasi-independent error. That is, the correlation decays exponentially as the distance measured by where the qubits are. So we assume that the model of errors is depolarizing. We assume that a certain error rate for memory and for gates, which might be different, and then we have assumption of that form. Now, in practice, we have to go and test if the error models that we have are of this quality or not, and then we have to adapt our error correcting scheme depending on this. The final things that we need is lots of qubits. Now, there I have to make a distinction by lots. For physicists, lots of qubits is more than a few. 3, 4, 5 is a lot of qubits nowadays. For computer scientists, lots of qubit is something which doesn't, or they would say it's not lots of qubits that we need because it doesn't go exponentially, it goes up only polynomially. But in the experimental world, we're not there at looking at this distinction yet between the exponential and the polynomial. So I mentioned lots of qubits. How many of them do we have around today? Here's a plot of the number of qubits as a function, of time. Around the 1990s, there's very few qubits. If you look at the top to see how many do we have, about a dozen, a little bit more than a dozen, 14 in ion trap, a dozen in NMR, and then ion traps, superconducting qubits, photons, and other devices, about 4 or 5 of this area. Now you can look at this and get discouraged. You can look at this and being very encouraged. The encouraging piece is that there are many devices that manipulate many qubits. The discouraging part is that we have only 14 after having kind of working very hard for about 14 years. So it makes about 1 qubit per year if you want to have some law, and you wonder how long is it going to take to get more than this. Sorry? So the 14 qubits is an ion trap, and there they did not have full control on these 14 qubits, but they were able to make something like a cat state 0, 0, 0 plus 1, 1, 1. In NMR with the 12 in there, you could do anything you want with them, but the noise was relatively large. I'll show a molecule in a few minutes with a dozen of quantum bits where you tell me what you want to do, and we can go and do it. Now, the other part that I say that what is the progress in experimental quantum information is the amount of precision we've done for gates. So I mentioned ideas of error pair gates of 10 minus 5, 10 minus 4, 10 minus 3, which was quite a step 10 years ago where the error rate were 10 minus 2 or 10 minus 1. Today we have error rates which are 10 minus 5, 10 minus 4 for 1 qubit gate, and a little bit worse for 2 qubit gates, 10 minus 3, 10 minus 2. And again, I'll come back a little bit more in detail on this. And what I'm going to talk about, the specific experiments I'm going to talk about are the ones done in NMR. There's other experiments in error correction using superconducting qubits, photons, or ion trap, but I limit myself only on the NMR one, the one that I've been involved with. There will be 3 types of experiments. One with liquid state NMR where we have great control, some with solid state NMR where we have not as many qubits, but there's a possibility of scaling up and do full error correction, and also ESR using electrons to parallelize, and I'll come back to this. I take the slides to thank the students who've done the hard work in the labs to make this reality. The next thing that I want to talk is about characterizing noise in our devices. And I need to make a little point here, and one thing I'm interested in is to characterize the noise for specific ways and to think about the model of computation slightly differently than what you would see in the 101 of quantum information. In your lesson of 101, you would think about a quantum computer as a device which set up a series of states, let's say the state 0, 0, 0, 0, 0. And from this, we were going to manipulate them with 1 qubit gate and 2 qubit gates, and then we're going to measure them in the computational basis. Now, this is a great model of computation, great for computing the resources that we need. Although when we want to go to the fault-tolerant version of this, we know many codes on which there's a property for gates which are called transversal, which makes them relatively easy to deal with. That is, there's not more than 1 qubit for one error correcting code. There's not more 1 qubit that talks to another qubit in another code. And so take care of bad propagation error in a relatively easy way. But we don't know how to do transversal gate for the 1 qubit error, and then that needs quite a lot of resources to make them fault tolerant. And there's a slightly better way to reduce the threshold is to think about quantum computation in a slightly different way. Again, we're going to prepare 0 state. We're going to measure in the computational basis. But the sets of gates that we are going to do are gates which are part of the Clifford group, the one which preserve tensor product of Pauli matrices. For example, the control knot, the NMR transformation, or the NOT gate. It turns out that these sets of gates are not universal. That is, you cannot do any kind of unitary transformation with them, although they have very nice fault-tolerant properties. But we can make this set universal by adding one more step, the preparation of magic state. And if we are able to prepare these states, then adding these states with this, then this becomes universal. And as my talk goes on, you'll understand why I go again and explain this part. It is the direction in which we have gone down in the path. Okay, characterizing noise. Oh, this should have been, I guess. So how do we learn about the noise? So first, we'll be interested of thinking only about the memory of the quantum computer, and then we'll start to think about what happens when we add some gates. And we're going to focus on applying quantum error correction. So there are people, if you do experimental physics, you want to learn noise so that you can do certain things. And so the focus that I have is only about let's do things in such a way that we can apply quantum error correction. And also, something which is important is that we want to be efficient because, as you'll see in a second, the amount of the number of function that you need to characterize the noise goes up very fast. In fact, one way of finding the noise is to do full process tomography. If you have a system which is not isolated, you can think of the initial state going to final mixed density matrix through the use of cross operators. We're going to rewrite them in terms of the chi matrix, where in the basis where these operators are written in terms of tensor product of Pauli operators. So the idea of characterizing the noise is to characterize this chi matrix here. But if you go and look at how many parameters we need to describe a chi matrix, it goes up by like 4 to the 2n. Well, 4 to the 2n goes very fast. So for n equal to 3, it's a few thousand pieces of element. If you go for n equal to 4, and there's an experiment from David Corey's group showing this full chi matrix for n equal to 3, but I haven't seen one with n equal to 4. And then people, I think, probably don't want to give this to their graduate students to do, as it'll take quite a long time to evaluate this function completely. So, in fact, for n equal to 12, it will be impossible to understand the noise totally, completely. Like, that's not that different from the classical world also. To have, for a number of n classical bits, to find the exact noise is very hard. So then you want to know some approximation of what the noise is. If you're interested in doing quantum error correction, and you're interested in using a code which corrects for n error, and I'll take n equal to 1 right now, what I'm interested in is what is the probability of having 0 error? What is the probability of having 1 error? What is the probability of having 2 error? What is the probability of having 3 errors? Independent of which qubit has an error. Independent of if it's an error which is characterized by the Pauli matrix sigma x, sigma y, or sigma z. And the question is, can we find this in a way which doesn't take 4 to the 2n experiments? And it turns out that the answer is yes. That is, we can coarse grain these parameters in such a way that we can find them using a small amount of, or relatively small amount of resources. So the idea of coarse graining is equivalent of imposing a symmetry. So the basic idea is that we're going to look at the noise in our system, and we're going to transform the noise by operating on it in such a way that only a few of these parameters comes out, the ones which are related to probability of certain errors. For example, if we're not interested in knowing which qubit has flip or has had an error, we can just symmetrize the qubits. So we can implement this symmetry. Then once the protocol comes out, we'll just get the probability of an error occurring without knowing exactly which qubit has happened. If we want to then average over x, y, z, if we don't really care if it's an x error, a y error, or a z error, then we can average over z. And then we can do this with averaging over SU2. So some many years ago, I was at a meeting with Richard Cleve, and then he showed me how this could be done. And the idea is having a two design. So if we take the noise, our evolution takes the noise, averaging it over SU2, integrate over all group, then we can find what these values are, probability of having an error that occurs, or 2 errors, or 3 errors. Now, in the lab, I didn't know how to do this integral, but fortunately these ideas of two design transform this integral into a sum, where the sum here is over the Clifford group. That comes out again. For 1 qubit, we can think about the Clifford group as the sum of the symplectic group and the Pauli group. So we can take this sum here and then approximate it. And if you look at this, you'll see that if you average over the Pauli group, what you get is that you get rid of the off-diagonal terms of this chi matrix. And if you average over the symplectic group, then what you get is that U equali is the probability for having x, y, and z. And once you understand this, what you're left is the values of chi's, which correspond to the chi for 0 error, chi for 1 error, chi for 2 errors, and depending of which qubit has happened as an error, and dependent of if it's an x, y, or z error that comes in. So the protocol goes as follows. You start with a state which is 0, 0, 0, 0. You implement the symmetrization group in the Clifford group. You measure how many qubits. So you have a noise that comes in here. You average it with the Clifford group. You average it over the symmetry group. You start with the state 0. And what this noise would look like now is just a tensor product of Pauli operators, which is going to flip some of these bits here. And the probability of how many flips is related to the probability of how many errors that you have. There's a slight things and kind of combinatorics you have to take care of, because if you have a z error, it doesn't flip the bit. You won't be able to measure this. But the probability of the z error, we have equalized it with x and y, so there's just a combinatorics factor there. So from this, you repeat the experiments many times, and then depending on what is the precision of these error rates that you want, you go and measure the numbers of zeros and ones here, and then you get the probability of getting 0 error, and then you count how many times you get only 1 error, calculate the P1, etc. In fact, if you look at this here, you realize that you don't have to do the symmetrization here because you started with a state which is 0, 0, 0, 0. And at the end here, if you just count the numbers of bits which I flip, you don't need to do that symmetry group also. So we started with that state, makes it a lot simpler. It turns out, we'll see in a second, we don't have to do that last Clifford group also, because if you apply a Clifford group to the computational basis, it's just a change of basis. You can calculate this by hand in advance. So the only thing that you have is to apply the Clifford group first, and that gives you the probability of errors. Okay, so here's an example of this being done using a solid-state NMR, small quantum computer. We have 3 quantum bits, and we look at, first we engineer the noise and say, does this protocol work very well? If we have errors which are only Z1, Z2, so here we have only probability of 0 error is 0, because we apply Z1 or Z2. Probability of 2 errors should be 0. Probability of 1 error should be 1. We get some reasonable results. Same thing if the error would be only Z1, Z2. Same thing happens there. And then we can go and do it with the natural noise of the system and see, does that work very well? And then what you find is our first trial of the natural noise, we thought there would be a large probability for 0 error and 1. We realized that, oh no, the error for 1 error was quite large. We go back and say, where does this come from? It turns out that this quantum bit was not decoupled very well from, these are carbon atoms. These are our 3 qubit system. There's hydrogen here, which couple our system. We decoupled them using sequences of NMR. And then we were not decoupling them very well. We go then a second time and then get something which is much better. And this is in trying to do something which is the unit operation, which seems to be easy in many technologies. In NMR it is not, because the Hamiltonian is always on. So this is how good we were able to do the unit operation in that particular system. Sorry? So these are carbons, these are hydrogens, and these are oxygen. And the small quantum processors use only the carbon-13 of this molecule, which is malonic acid. So we use a crystal of malonic acid. I should point out that we have a molecule with 12 qubits. Hedy mentioned, asked the question a bit early on. Well, this is a 12 qubit system, which we have full control on, and then we're presently doing this process on this 12 qubit to understand how well it works for a larger number of qubits. Okay, we can adapt this idea to benchmark Clifford gate. Do this not only for memory. So we look at what the process that we had here. So starting the protocol we had, making the state 0, 0, 0, 0, the noise is here, applying these Clifford gates, and then measuring in the basis. Now it's not that hard to look at this and say, oh, what happened if you would be interested on benchmarking a gate U? We had U and U dagger, and if U is a Clifford gate, then we can absorb this Clifford gate on the second Clifford gate, and this is efficient classical computation, and then we can absorb this in the measurement in the different bases. So we don't need to do this in the quantum computer, and then the noise kind of applies to that gate, result in a protocol where we start with 0, 0, 0, we do the Clifford gate, we do the gate that we want to benchmark, and then we can measure there, and then we can do this again with the same small quantum processor. We can do, again, looking at what happens when we do nothing, benchmark that gate, or when we do one specific Clifford gate, which corresponds to the encoding of a 3-bit error correcting code, and then you get some fidelity which are kind of reasonable, and I'll come back to some of these values. So with this, we're able to benchmark and to assess the amount of noise when we have the memory, when we don't do anything to our quantum computer, or when we do certain types of gates. But with this parallel benchmark, we are not able to distinguish the errors that comes during the process and the errors which are created because we have imperfect initial state, imperfect measurement. And so one way of asking the question of, can we distinguish both of them? Then we can do this with a slightly different protocol, one which was suggested by Manik-Nil. And then the idea is that we'll be able to find an error per gate, which is independent of the imperfection of preparing the initial state in the measurement. So the idea is the following one. We're going to, again, prepare a state, which will be something like the state 0, 0, 0 again. We're going to do some Clifford gates, a series of Clifford gates, and this benchmarking is only, again, for Clifford gates. And then we're going to reverse the series of gates that we do, make a measurement, and when we're going to do more and more of these Clifford gates, okay, and then we are kind of do a random set of these Clifford gates, one after the other, when there's, let's say, 3 of them. That's why here, when we look at the fidelity as a number of gates, we have a dispersion of them. So this, for a 1-qubit gate, this could be an X rotation, a Y rotation, and another X rotation. We can reverse it. If this would be perfect, we would get exactly the same state to start with. But in practice, you don't get this. And then by making a set of those instantiation, then you can draw a line between the fidelity as a function of time, and this line is independent, or at least the slope of this line is independent of the state preparation errors, the measurement errors, and gives us an idea of what is the error rate per gate for this system. Here's this benchmark applied to different systems, and you can see error rates which are 10 minus 3, 10 minus 4, 10 minus 5. There's other technology also which has error which was worse that I've not shown in there. But it's quite encouraging to see that the error rate per gate, and this is for a single qubit gate, gets to values which are kind of seems to be reasonable and slowly going to this values that I mentioned in threshold that we had. Now, one warning, if I talk about the threshold here, is that these are for 1-qubit gate only, and they are also set up in systems which are the best to do 1-qubit gate. For example, in the ion trap, they have a single ion in the trap, so they don't do this with their 14 ion in the trap or 2 or 3. For the liquid state MR, we have a molecule with a single nuclear spin in there, and so it's relatively easy to do. If we go and do this for our 12-qubit molecule, it would be worse, a little bit worse than this, maybe 10 minus 3.
So what do the numbers look like if you have 2 or 3 ions?
Nobody has done this this benchmark for 2 or 3 ions put together, but you can deduce it when you look at the number. If somebody has an algorithm, you assume that okay, the algorithm has no bias in one way or the other, and they do 10 gates, 1 qubit gates, and 10 2-qubit gates, and some values. And I mentioned about 10. So it is the benchmark of Clifford gates, okay, where you do an average over all the Clifford gates. So you average over all possible Clifford gates the same way as I was doing the average over SU2. So what other so when you think, is there another symmetry? Okay. Okay. This is an example of benchmark for ESR. I'm probably kind of run out of time, so I'll go a little bit faster. Here's some fidelities for, what? Yeah, but I still have quite a lot of slides. I will come back to you in a few minutes and say, you told me I had a lot of time. So here's 2-qubit gates, which is, except for the first one in liquid state NMR, those are not the generalization of the benchmark, but an estimate of the 2-qubit errors for some system. So here, a few times 10 minus 3, 10 minus 3, superconducting. So that's a little bit old. That was about 10%, and I'm sure that John would say today it's much better. And NV centers about 10% also. Linear optics, neutral atoms, and you can see things. It would have been great if we would have a same table in the years 2001, 2002. So you would see we would be 1 or 2 order magnitude off this. That is, things like neutral atoms 10 years ago, the error rate was pretty much kind of 1 error per gate. Now your things are getting better, and I expect in the next 5 years that this will go to the 10 minus 3 in many technologies. Okay, so I talked about the noise, how to estimate it, and the summary of this is that we have an efficient way of characterizing the noise in systems, and we have started to try to do this on different systems in a systematic way and having the ability to compare different technology. What I want to do in the next few slides is to give example of quantum error correcting code. So there's probably a few tens of papers of different codes being implemented in different ways with different error models. Most of them are systems where people put errors by hand. So they implement the code, put the error by hand, and show that they have the right control to do this. I think there's very few, and I think maybe this is set of very few, where we take the error which are the natural error in the system. In NMR, the T2 errors, the dephasing or the Z errors, happen at a time scale which is a bit faster than the bit flip errors, about a factor of 10. So the idea is if you correct for the phase error first, then you are able to do something, and then you say, next time when we're kind of better control, then we can go and correct for generic errors. So if we have only phase error, there's a very simple error correcting code, which encode the one state into a state which is the form alpha plus 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 beta minus minus minus, where the plus is 0 plus 1, minus is 0 minus 1. Decoherence happens, then we decode, we do the error correction, and then we look at how much we recover the information. So a bit more than 1998, 15 years ago, we implemented this error correcting code using a molecule which is called trichloroethylene, 2 carbons, 1 hydrogen, relatively well isolated. And then what we could show is that if we don't do error correction, there's a red line here which shows the decay of the fidelity. If we do error correction, we see something which flattens a little bit. I should mention here is that on this axis, maybe is what is called the fidelity of entanglement, which is the fidelity that a state would have if we take 1 qubit, we send it through the channel, and then there's another qubit which is entangled to the first one, which nothing happens to it, and then we take the overlap between the final state after the noise happened to the first state. So it gives you the idea of how much quantum information can be transferred through that channel with or without error correction. It turns out that this property of fidelity of entanglement depends only on the noise of the system and the system itself. And you can think about it as also the probability of sending the unit matrix and how much of the unit matrix is left at the end, how much of the x operator, how much of the x operator, the y, and the z operator, and take the average of these four input. And so if you do this, you get the curve which is of this form. And the demonstration here of error correction is to show that the error rate is not epsilon anymore, which is what you would have in red for a small amount of time, but something which is proportional to epsilon squared. So we've corrected 1 bit error in there. Well, we have not done this exactly, because here's the 1 bit error goes like 1/10 of t. Here we've reduced it about by a factor of 10. And this is the demonstration that we had enough control to help a little bit in here. The second thing that you can see is that when we start here, we didn't start with a fidelity of 1. We get a fidelity which is 0.85 when we don't do the error correction, which is the Toffoli gate here. And we get 0.8 when we do the error correction. And so the 20% of fidelity that we've lost is the error that comes in when we do the encoding here, we do the decoding here, and that gate there. So this is something that has to be corrected and improved. And more recently, I had an undergraduate student 3 years ago, in which I told him, go and do this exact things, but with all the tools that we've learned in the last 10 years. For example, there's something called RF selection, improving the signal by having a greater RF homogeneities of the signal to hit the atoms, using also something which is called grape pulse, kind of increasing, kind of not going by gate, but saying numerically what is the RF field that we need to implement a gate of this form, and find them numerically, and doing pieces, what we call pulse fixing. That is the amplifiers that we have a little bit of nonlinearity, and so we bring a little coil next to our sample. We look at the RF field which is emitted, we kind of look at it, and then we correct with what we expect it should be, and then make a little loop like this, and that improves this. And I'll give another example of this in the future. And with all of this, we were able to improve the fidelity by a factor of about the error being decreased by a rate of about 20. So without error correction, we get to 0.99, 0.98 on error correction, and then we've also improved by a factor of 3 or 4 compared to what we had here on the first term that comes in there. So here's one first demonstration of part of error correction, and I say part because if we could have pure state here, like the 0, this would have been a demonstration we could keep the information better. In NMR, we have these systems where we have to do something which is called pseudo-pure state. We have to create these states. Turns out that it takes out some signal, and then we take a hit by this, which is not really reflected in here. It should be about a quarter of all of this. So this is one of the problems that we have. This demonstration is really a demonstration that we have the control once we'll have the pure state, and I'll come back of how do we get the pure state in a few minutes. We can also do here an experiment in the solid state version where we did twice the error correction. So we start with this pseudo-pure state dimension, we do quantum error correction once, then we go back, we decode, we do the error correction, we create another pseudo-pure state, and then we do encode again, and then we look at, is it better or not? So if the error rate is very fast, then you'll be better to correct twice. And if it's very slow, then you might be okay, because the second order term comes in there. When do you start to gain by doing this? You can see it from this curve. If you don't do error correction, you get the blue line in here. You do error correction once, you get the red line. You do error correction twice, you get the black line. So at small time, then you don't gain by doing twice error correction, because you do more gate by doing error correction, and you get a hit on the sensitivity, the fidelity when you do this. But at the long time, then you start to gain, because the second order term starts to come in. Doing twice error correction kills a little bit of it, so you improve by doing this. So we're getting there slowly on getting the control to do multi-rounds of error correction. I mentioned doing error correction with for correcting for phase, but in general there will be errors which comes from bit flip also. So some years ago we did the 5-qubit quantum error correcting code, which is the smallest one, which corrects for bit flip and phase flip at the same time. Now you can see the encoding is a little bit more complex than what we had before. So you remember this was the encoding for the 3-bit code. The decoding is the inverse of this. And then the Toffoli gate turns out to be 3 2-qubit gate, or no, 5 2-qubit gate. Now, if you look at this code, a lot more complex. This is encoding. The decoding is the inverse of this. And then the error correction is the kind of product of doing this, correcting for Z error. Then you have to do correcting for the X error, and then correcting for the Y errors. And then all of this give you a state which should come back to what you started with, alpha 0 plus beta 1, whatever it is. And so here's a distribution, the difficulty for the different errors, putting an error, let's say no error, a Z error on the qubit, which is here, the sum of the three hydrogen atoms here turns out to be equivalent to spin half. Error on carbon 1, carbon 2, carbon 3, carbon 4. So some of them we get error which are infinity, which are about 73% on average for all of this. Now, we would like to do this again, but now with the natural errors, not the errors that we put by hand, which is something that is typical of these implementation of error correction. I mentioned about reducing the entropy. If we would have a magic projective measurement, then once we do the error correction, then we can reset our qubit to 0 and go back and kind of do a second set of error correction. We cannot do this in MR at present, but here's a way that going towards the ability of being able to do this. And the idea is to cool some of the qubits in a way which is not that different from what I think of Maxwell's demon, by looking at the state of the system, doing a computation on it, and then so that you can isolate the entropy in some subset of the qubit and then cooling the other qubits. A simple example of this is one with 3 qubits. So if you have a polarization which is epsilon, it's possible to decrease or increase the polarization of this to 1.5 epsilon at the prices of heating both of them. If there's the ability of connecting to a bath, we can cool them back to epsilon, then do the process again, go back to 1.5 epsilon. And it turns out that if the polarization is epsilon, and if we have n bits, if epsilon is smaller than 1 over 2 to the n, we will polarize up to some value which depends on n and epsilon. But if epsilon is greater than 1 over 2 to the n, then we can polarize up to the value 1. So the experiments I'm going to show was at an epsilon which is 10 to the minus 5, and we're going to use only 3 qubits, so we're just kind of increase the polarization by a factor of 2 if everything would be perfect. But if we go to high polarization, polarization of order 1, then we just need a few qubits to be able to do this. And in my last slide, I'll mention this again. So here's an example of implementing this idea of algorithmic cooling. So we have a molecule again of malonic acid, with 3 carbons, and we are able to couple the bath, and here the bath is one of the hydrogen atom. So some years ago, I thought that the idea of coupling to a bath, increasing and decreasing the coupling of a bath, would be something which would be extremely hard to do. But it turns out that in the sparkler NMR system, it is possible to do, as we are decoupling the hydrogen atoms using refocusing sequences. And it turns out that this sparkler hydrogen here is coupled in a much stronger way than all the other hydrogen. So we can decouple all of them with a certain power of the decoupling. And by reducing the power of the decoupling, we can selectively recouple between this hydrogen to this carbon here. And then so we can make swaps of the state of that hydrogen to the one to this carbon, which is what we write here in the blue part here. So the algorithm goes that way. We first get rid of the polarization on all of our qubits in here. And then we first kind of transfer the polarization of the hydrogen to the carbon. We get rid of the polarization on all of them because the polarization of the hydrogen is 4 times than one of the carbon. So you told me I had a lot more time, and now you tell me I have 5 minutes only.
A lot more time to go.
And then we swap, once we transfer the polarization of the hydrogen to the carbon, then we can send it to one corner there. And then while we do this, this hydrogen here rethermalizes with the bath. And then so it does this in the red here. Then we can transfer the polarization again. And once it arrives to the carbon in the middle, then we can send it to the right. And then we can do this a 3rd time. And then we do this algorithmic cooling process. And then we get the value, which ideally we should be 1.5. And life is imperfect, so we get only 1.39. So we go and do this a 2nd time. We use the same process, thermalize with the bath again, transfer from the hydrogen to the carbon, and do this a 2nd time. 2nd time we should get 1.75, and then we get 1.56. So we've polarized a little bit more, 3rd time, and then 4th time is there. And then if we try to do a 5th time, because of the error that we have here in the particle system, it tapers off to about 1.7. If the world would be perfect, in that particular case would be 2. By working a little bit harder, I think we can probably bring it to 1.8, 1.9, and doing this. And this will be something which will be useful, I guess. I was going to talk about magic state distillation. I think I'll just say that it is possible to do magic state distillation. The idea is if we have a state of this form here with p is equal to 1, then we can add this to our set of tools for quantum computation because we are using only Clifford gates, and we can compute with this. But in practice, these are not going to be perfect, and so we need to find a way to purify them. And the magic part of this, at least the way I understand why KDF and Brevi called it magic, is that we can purify them using only Clifford gates. So we can use our fault-tolerant gates that we would have in the future, use them, and then take a set of these imperfect ones, make a measurement here, and we'll get rho with a higher value of p if p is greater than 0.65. And so you can distill them, make them more precise, and then use them for quantum compute. And demonstration here that we could do it a little bit better is the demonstration here that we're above this right line. The black is theory, if everything is perfect. The red is the simulation with the decoherence that we have in our system, and so with the Hamiltonian, and then the black line, the black little dots is what we've succeeded in achieving. So we would be able to do magic distillation in reasonable system. Okay, I must be nearly at the end. So I mentioned how to kind of characterize the noise, how to do error correction, how to do magic state distillation, and algorithmic cooling. Most of them were nearly there to do many rounds of quantum error correction, except for doing algorithmic cooling at where we get pure states, very near pure states. So how are we going to modify our system so we can reach this? So the idea is to use something, again, like malonic acid, but we're going to create a defect with an electron here. Everything that I've mentioned was done at room temperature with very low polarization. But if we go to reasonable field, then we can polarize this electron to an order about 0.1, kind of 0.1 to 0.2. When we arrive there, we can use 4 of these qubits and boost that polarization of 0.1 to something which is very near 1, and then do the error correcting scheme. And then while we do this, the electron will get repolarized. It gets repolarized fast compared to the gates that we do in here. And this is what we have started to do at present. So for this, we have to change the type of equipment that we have. We can not use the NMR spectrometers that we've had, but we have to use electron spin resonance. Here's part of the probe that we have, build the new resonators, and then result of this, we should know. Maybe in the next conference of the QStart, I could come and give result on this. So to summarize, to implement error correction, we have to have a good knowledge of the noise. We have to have good control, the ability to extract entropy, of course, ability of doing parallel operation. Recent experiments have demonstrated that these elements individually, but we need now to put them together and show that we can control quantum information at a time scale larger than the natural time scale of the system. And I'll end by saying that it's only the beginning. Thank you very much. I think you have to turn it on.
So basically, the question I'd like to ask regards, you mentioned the 12-qubit molecule. So at what point will frequency crowding be a problem? Basically, in the Zen sense, you're manipulating a marionette with one string, just with many, many different frequencies. But ultimately, there's going to be a problem with crowding, isn't there?
Absolutely.
So how far can we realistically go with
I
these
think we
controls?
We could probably double the number. Again, it depends in NMR compared to other technology. The difference, the way we address this is through frequency space. And as you mentioned, certainly if the frequencies becomes too near between the different carbon, then we cannot address one without touching the other one. Then the question of finding a right molecule is part of luck.
An open problem.
And
you need a quantum computer to solve it.
I don't know. Even if we would have a quantum computer, or maybe we could test, make the simulation and say what would be for different molecules, and then think about how we would synthesize this. Part of this is found by looking at huge books of molecules, looking at this, and most of them don't work. So then you find one that works, you synthesize them. My friends, the chemists, always say it will take 2 months to do this. It always takes longer than this, about a year or two. Finally, we have a molecule like this. We can, this one is incredibly well behaved. There's about a kilohertz, at least, between each of the atoms, which, thinking of the 2-qubit gates are about 100 hertz, it gives us plenty of room and kind of no problem. The frequency crowded is not the problem in here. The problem that we get here is the T2 time divided by the gate time. So the gate time is 100 hertz, the T2 time is about a second. So it's about a factor of 1%, and this is what, at the end, gives us a hard time. And now I go back and look at the control that we have on the gates on NMR compared to any other ones. It's truly outstanding on a 12-qubit. Other ones will build up, all the technology will build up, but meanwhile we can learn how to learn certain things, give tricks. The work on these great pulse, kind of shaping the pulses, is something that we started to do in the year 2000, and NMR people were doing this much before, but for quantum information, and now I see all technologies are doing this.
So you mentioned that you characterize the noise, and we all know that, for example, noise that causes dephasing or decoherence should be represented by a spectral function. You want to know how fast it changes, and you mentioned that. But then you show this characterization of the Clifford gate using benchmarking, and you sort of randomized the sigma x, sigma y, sigma z, although they come from very different origins probably. And then this probably represents some kind of a white noise model. So I wonder whether the spectral properties of noise are relevant also to gates as they are relevant for decoherence memory.
So that's a very good question. If I talk to my friends, the physicists, they will want to me to give them the spectral noise density. If I talk to my computer science friends, they don't care about the spectral density. They want to know how many errors per gate so that they can implement their quantum circuits. So implicitly in these P0, P1, P2, hidden is an integral over the spectral density. I don't know how to turn properties of the spectral density into error correcting codes. But I know how the probability of 0, 1, 2, 3 errors can be taken care of from error correction. If I want to improve on the control of my Hamiltonian, then the spectral density is a useful piece. So you know what is the origin of the noise, and then you can try to find ways to mitigate that particular piece. But we know that you will never be able to have a scalable device by just improving the control the hardcore way by improving the quality of the Hamiltonian so this will be exponentially hard. And we can see it in a molecule like this, for example, that you hit this. So on the first step, when you first learn your system, this is a very useful piece of information. When you want to scale, then it will not be.
So just to follow up on this question, do you know that with this type of characterization of the noise, the threshold theorems work with the same, is this the right number to plug it in?
So I think it is the right number, but I don't have a proof. And it is...
So about the algorithmic cooling, can it be used in medical NMR to improve the equipment?
Yes, I think that there's a possibility of this, but you need to, so you cannot do it just randomly. You might be able to, if you have a large molecule and you do liquid state NMR, you can do one step, help a little bit. But I'm just going back to that slide. Okay, when we do this in here in a solid state system, you needed to have a certain set of properties put together, which maybe for medical reason it's not useful, or the molecule that you're looking at is not set up in that way. We needed to have a crystal of something. We needed to have an hydrogen here, which has a certain property that this one could have a much higher coupling than the other one, and there it did work. So now I'm saying this without having really kind of look at what do people do in medical imaging and what kind of molecules they are using, and is this a possibility of using this and bumping it. So definitely worth doing. My colleague David Corey has used an idea of that was developed for NMR quantum computing using RF selection, which has been applied to oil exploration. Field totally different. I would have never thought that ideas of quantum information would have an impact on oil exploration. 10 years ago, I would have laughed. But today, Schlumberger, the company who makes tools to image oil wells by sending small NMR machine, are using these ideas in their product. So I think it's definitely worth having a look.
How are they using it?
So when you try to do NMR quantum computation, you get stuck on the fact that you are using an ensemble, and the RF coil that you send and the RF field that you send is not homogeneous. So some of the molecules here sees a slightly different field from there. So when you start to do something like the benchmarking, then this leads to an effective decoherence. Okay, because the different qubits do slightly different things and they cancel us. Okay, so what has been done was to find a way to select piece of your sample which has a certain homogeneity to a certain level. So you tell me 1%, 2%, I'll give you the algorithm to kind of select the sample. And you can image that sample, that subsample in there, and it's a really funny, weird shape, which is not that easy to understand. So what the oil exploration people do is that they send a small MRI machine at the bottom of the oil well, and they want to image the side of the bore, and they want to answer a question like, is it oil or is it water that is there, the liquid? Is the rock porous or not? And is the fluid moving or not? So with small MRI machine, they can know this. With the homogeneity that they have, they can go to about 2 centimeters from the bore. And it turns out that that piece of information is enough for them to pay the price of sending the small MRI machine. With these new ideas of RF selection, you get a signal which is lower because you look at a smaller amount of things, but the signal to noise ratio gets much higher. And it can go apparently to 8 or 9 centimeters instead of 2. And for you as a computer scientist, going from 2 to 8 is just a...
I imagine if I were an oil driller, that would be very important.
That's it. And so it costs millions to draw. So here's an application of quantum information to the oil industry, which is totally mind-boggling to me. But it's a practical one.
So let's continue all the rest of the questions during the coffee break, and we'll be back at 11:10. And thank you.